Welcome to our Math Vodcast for Group 37. In this video tutorial we will aim to cover the basics of position, velocity and acceleration as well as their antiderivatives. Let's get to it. First let's look at the derivatives from position, which is where the speed equals 0. We write st, which is our distance as a function of time. If we then take the first derivative of speed, we get the velocity function. Now this is where it gets interesting. By taking the second derivative of speed, not only do we get the first derivative of our velocity function as seen before, but it can also be shown as the acceleration as a function of time. So from this we can see how all three functions relate to each other. Now let's look at the antiderivatives or integrals. Similar to what we did before, working from speed to acceleration by differentiation, we can also move backwards by taking the antiderivative. Hence the antiderivative of acceleration, which is written as the indefinite integral of acceleration as a function of time, is equal to our velocity function. And likewise, the antiderivative of the velocity function gets us to our speed function, or our initial position when t equals 0.
The formula for a constant acceleration in relation to the velocity can be demonstrated when we substitute velocity in relation to time with -8. When t is equal to 4, we substitute this into the first step of the equation, where you get the line vt equals 3t plus c. First, we have to find a constant in order to answer this, therefore we add in the variable c. Vt equals 3t plus c. We can then continue to answer the equation by substituting in the number v4 equals 3 times 4 plus c equals -8. This allows us to find the variable c, which equals via a two-step process, which is v4 equals 12 plus c equals -8, which then c equals v minus 20. This allows us to discover the velocity in relation to time, as we can substitute minus 20 into the c section of the equation in order to get vt equals 3t minus 20. Position st equals the integration of vt dt equals r times 3 times t squared minus 20t plus c.
When we enter the formula for constant acceleration into a real-life scenario, we can gain an understanding as to how it may relate to this scenario. If we look at a scenario that has a swimmer diving into a pool, we can use the equation Vt equals -t squared plus t10 in order to find the athlete's location after a period of time. In this circumstance, it is 3 seconds. In order to answer this, we first have to set the parameters for svt dt, which is 0 and 3. We then have to integrate the expression from vt into the equation, which will make it equal -t cubed on 3 plus 5t squared. You then evaluate the integral between the time limits of 3 and 0, which would be -3 cubed on 3 plus 5 times 3 squared minus 0 equals 36 meters. We see the athlete has a linear increase of velocity from 0 to 3 seconds and a constant acceleration.
Although often overlooked, mathematics plays a very important role in sports. Whether it be a coach's formula for drafting players, discussing players' statistics, or like our example of the Olympic swimmer, using fundamental theorem of calculus and integral calculus to predict race outcomes, or in researching biomechanical aspects of sport to enhance athlete performance. In 1973, mathematician Joseph Keller used simple dynamics and integral calculus to determine the optimum race strategy and pacing for short running events like the 200 metre and 400 metre sprint. In addition to the positive social implications of calculus in sport, mathematical models are often developed and utilised to avoid ethically difficult or environmentally damaging experiments. Whether it be in sports to anticipate a swimmer's position at a given point in time, or in mathematical models for research, it is evident that the application of position, velocity and acceleration using integral calculus has had countless implications in society, and with further developments in technology, will continue to aid in the observation and development of our society and the world.